Welcome to the podcast summary of Dive into Lazy Stacks and Scrolling with SwiftUI from WWDC 2026. Today's thread is SwiftUI Lazy Stacks, and a lot of it comes down to one simple fact. Lazy stacks are smart, but they're guessing more often than people realize. That guesswork shows up in scroll position, visibility rules, performance, state, and even whether a view vanishes a little too early. The good news is most of the fixes are pretty practical once you know what the stack is actually doing under the hood. A lazy value stack doesn't know the exact size of views that haven't been laid out yet, so it estimates the height of off-screen items from the average size of the ones it has already measured. That means total content height can change while you scroll, because every newly measured item gives the stack better information. Usually that just feels like tiny adjustments, but after something like an orientation change from portrait to landscape, the estimates for all the content above your current position can be temporarily wrong. So if things look slightly misaligned for a moment, that's not your app losing its mind. The stack is recalculating space it had to approximate earlier. There's a nice upside to all this laziness. If you put a lazy H stack inside a lazy V stack, the outer vertical stack can delay building that whole horizontal section until the user actually scrolls down to it. That's great for something like a photo showcase, because people who never reach it never pay the cost for it. One catch is sizing. The lazy H stack takes its ideal height from its first subview, so if later items have taller captions, those captions can get clipped. The fix is pretty straightforward. Give the row a fixed height, or constrain the text with line limits so the stack isn't surprised later. One of the stranger bugs here comes from scroll transitions. If you apply a dot scroll transition that physically moves a view outside its original frame, the lazy stack can decide that view is off-screen and recycle it early. That's the pink swan step view problem in a nutshell. The animation looks cool right up until the view disappears before it should. If you swap that positional movement for something like a scale effect, the view still animates but stays within its estimated frame, and the premature disappearance goes away. Variability-based UI can also get shaky if it depends on estimated offsets. With dot-on-scroll geometry change, you're watching a content offset that can drift when the lazy stack updates its size estimates, so a button that should appear at one threshold may suddenly trigger at another. Using dot-on-scroll target variability change is more stable because it keys off whether nearby subviews are actually visible. So if your rule is that something should appear when another item is 80% visible, that rule stays tied to real visibility instead of a moving estimate. A subtle performance issue shows up when a leaf view sometimes returns 0 subviews based on an environment value. If a step view conditionally disappears that way, the lazy stack still has to preserve earlier indices, which means it may keep that view alive longer than you'd expect. That adds extra evaluation and memory cost, mostly because the stack can't fully trust how many subviews exist at any given index. Filtering at the model level fixes the root problem. If you trim the array before the for each or use a Swift data predicate, the lazy stack gets an exact deterministic view count. That's cleaner for performance, and honestly cleaner for your future self too. Lazy stacks also do something helpful. That's easy to miss. They pre-evaluate the body and layout of views that are about to enter the visible area. That spreads expensive work across frames so fast, scrolling is less likely to hitch. If you've got heavy setup, like loading diagram data, it's better to kick that off in the view's initializer rather than waiting for appear. Because by the time appear fires, the user is basically there already. Prefetching gives you a chance to have the work underway before the view actually hits the screen. Another important mental model: a recycled lazy stack view is disposable. If step view owns a local state variable, like is highlighted, that state can vanish once the view scrolls far enough off-screen and gets reclaimed. From the framework's perspective, that's memory doing exactly what memory is supposed to do. From the user's perspective, it can feel like the app forgot something obvious. Persistent state belongs in a model object or a binding owned by a parent, where it can survive view reuse. Programmatic scrolling by ID is fastest, when each for each element resolves to one subview. In that setup, the lazy stack can compute where the target lives without constructing a bunch of intermediate views, which is exactly what you want when you're animating a jump. It also helps to avoid layout changes that happen after appearance, like geometry-driven state updates that alter sizes or positions. Once those post-appearance changes kick in, the stack may have to recompute content offsets, and that's where smooth animated scrolling can start to feel a little mushy. A lot of these issues point to the same broader lesson. Lazy stacks do best when the structure is predictable. Stable view counts, stable frames, stable identity, and state that lives outside recycled views all make the system's estimates more accurate and its optimizations more effective. When you push conditional logic down into leaf views or animate views outside the frames the stack expects, you're basically feeding uncertainty into a system that already runs on partial information. And to be fair, it still does a pretty impressive job. It just appreciates clear instructions, same as the rest of us. So if a lazy stack ever feels a little haunted, it's usually not random. It's estimation, recycling, or both. Once you design with that in mind, a lot of the weirdness turns back into performance. This episode was generated by Podkey. Create your own at podkey.fm.